Ana Claudia Nabarro from Sao Carlos. Asymptotic direction of spacelike surfaces in the C35 space.
First of all, I'd like to thank the organizers and to give me this opportunity. And also it's a pleasure to participate of this workshop in honor to Federico, that I think we met at the first time in Valencia in 2006, where we both were visiting Carmen at that time. Congratulations, Federico, for your birthday. And this work is a joint work with Masaki Kazedo from Japan and Maria Ruas and sorry, this is not works. We published a paper in 2015, and I will give some preliminaries and talk about the spacelike surface in the C35 space, second fundamental form, asymptotic directions, and some geometry. Some results about invariants, classification, number of asymptotic directions, some examples, and a work in progress where we are studying some properties and the singularities related to the equation of asymptotic directions. We work in Minkowski space, where the metric is given by the inner product of x, y, and where we have a minus in the first coordinate. Then we have that x can be a vector spacelike if with x by x is greater than 0, light-like if x by x is equal to 0, and if this is less than 0, we call time-like vectors. Then we have pseudospheres, and we're working in S1n, that is called the de Sitter space, where x by x is equal to 1. We have the light cone of the light-like vectors, and we call by x the embedding of the space-like surface in the C35 space. And we have a time like in space-like autonomous sections, OM, that we denote by N0, N1, and N2. The light-like vector, light-like normal vectors, we denote by E. They are in the light cone, and you can represent them by N0t plus cosine theta N1 plus sine theta N2. Then the second fundamental form at a point U has the AI, BI, and CI, has the coefficients of the second fundamental form that are given by the projections of the second derivatives of the parameterization in the directions of the normal directions. And the second fundamental form is written by this formula, where we have the new coefficients, and we call by L, M, and N. And these are given by the 3x3 matrix of the coefficients of the second fundamental form. we denote the matrix, the 3 by 3 matrix alpha of the coefficients of the second fundamental form, and then we have another matrix, the 2 by 2 matrix with the coefficients of the second fundamental form of the equation, and the asymptotic directions. Everybody knows that is studied for surfaces in R3, and it is introduced in R4 and the R5 case, and there gives some examples. Little introduced the notion of a curvature ellipse, which gives some geometric invariants. Mochida, Romero Fuster, and who was studied surface in R4, and its inflection points with Ronaldo Garcia, and also in R5. Romero Fuster, who was in the TARI, studied asymptotic curves on surface in R5. And Federico and Bayard study, for example, surfaces in R5 and in R3-1, where appears also the curvature hyperbola. Then, at a point of the surface, and if you have a direction given by theta, and V in the tangent space, then V is asymptotic direction on M if and only if the equation of the second fundamental form in V is equal to 0 for some binormal direction theta. That is, that theta is such that delta of the equation is the discriminant of the equation is equal to 0, theta equal to 0. And we remark that the for the first group, we have coordinate changes on M by a diffeomorphism that is given by a composition on the right side. And for the second group, we change the normal sections on M. And we know that we prove that the signs of delta and the ranking of alpha are invariant on the actions on these actions of G. To have some geometry properties, we consider a cone and the LM ellipse. This cone is not the cone of the light-like direction, but this is given by vectors in R3, such that m squared minus ln is equal to 0. Then we have that the rank of the second fundamental form is 2, the 2 by 2 matrix. If and only if ln is not in this cone. The rank is 1 if this is ln is in the cone. That means that delta is equal to 0. The rank is 0 if LMN is the origin. And if we consider alpha the 3 by 3 matrix of the coefficients of the second fundamental form, then we call LMN ellipse given by E theta equal to LMN we can represent by A, B, C in this form. Here, A means the center of the ellipse, And BC described this. Theta is binormal if and only if E is in the cone. And P is an inflection point if there is some theta such that the ellipse passes through the origin. This means that the rank is equal to 0, and all directions are asymptotic in this case. P, we call P a conic point if the ellipse is on the cone, and in this case, all directions are binormal. Then we have some types that we call a vector LMN is elliptic if it's inside the cone, hyperbolic if it's outside, and or parabolic if it's on the cone. If U is not the inflection point, then we say that alpha is elliptic or hyperbolic if and only if the vector A is always elliptic, hyperbolic, under the action of G. And this means that the interior of the ellipse consists of elliptic vectors or hyperbolic vectors. We have the geometry. And otherwise, we call alpha a parabolic. If the vector A is neither a elliptic or nor a hyperbolic, there is a mistake here. Well, then we classify also when the case alpha equal to 1, but we use here alpha equal to 2. We emphasize alpha equal to 2 and 3. In this case, the vectors A, B, and C span a plane by the origin, generated by X and Y. These determinants, if you consider the sign of these determinants, then we have the cases of M2 hyperbolic if the 2 is less than 0, or parabolic or elliptic if the 2 is greater than 0. The 2 and the type of the plane are invariant under the action of G. The sign of the 2 determines the position of the plane with respect to the cone. And the ellipse is on this plane. Then we have some geometry about all the cases. The plane that cuts the ellipse here transversely cuts transversely the cone, and the position of the ellipse in the case high elliptic is inside the cone, or hyperbolic is outside the cone, and the parabolic, the other, if it's not a elliptic or a hyperbolic, and the inflection point when the ellipses pass through the origin of the cone. And the M2 parabolic, the plane is tangent to the cone, then we have a line, and the ellipse is outside, the interior of the ellipse is outside the cone, or in the case parabolic, the ellipse meets the cone, here, a parabolic. And the inflection case when the ellipse goes to pass through the origin. And the case M2 elliptic. The ellipse is outside the cone. And the inflection points also here, the same. We work with some normal forms. For all the cases, we have the normal forms for the rank 2. And consider the normal forms, we have the cases. And for each case, we study the number of asymptotic directions and the number of binormal direction also. And here we have inflections. If this is multiple solution, then we denote by 2 type, and so on. The M2 parabolic also, the number of asymptotic and binormal, and the M2 elliptic case. If the rank of alpha is equal to 3, then the ellipse is on the plane BC, that's outside the origin. Then we don't have inflection points. We have all the cases, A elliptic, A hyperbolic, and A parabolic, and the normal forms. The equation of the asymptotic directions is a binary differential equation, but it is a quadratic, where the Ki depend on the coefficients of the second fundamental form. For surfaces in R3 and R4, the asymptotic direction are given by a BDE in D1, D2. The coefficients depend only on the coefficients of the second fundamental form. And in the case in R5, the equation is a kinetic form, and their coefficients depend on the coefficients and their derivatives. Here we have Ky given by this formula, where A, Y star, and so on are cofactors of the matrix of alpha, the matrix alpha. And we have that in the rank 3 cases, we have the number of asymptotic directions can be 0, 1, 2, 3, 4, or infinity. There is no inflection point because the ellipse does not pass through the origin. Infinite asymptotic direction at P means that the LMN ellipse is on the cone, then all normal directions are binormals, and all tangent directions are asymptotic. That is the case where P is a conic point, which binormal directions indicates different asymptotic directions. Then, to study the type of asymptotic direction, when it is a finite number, we study the type of binormal direction by using the equation of the discriminant. The rank 3 case, we have examples. Consider the Monge form of the surface in the de Sitter 5 space, given by this equation. If you consider F, G, and A in these formulas, then A, B, and C are the coefficients of the second fundamental form. And in this case, all directions are asymptotic, and all normal directions are binormal. That is the conic point. In the second example, we have other F, G, and J, and the asymptotic direction are given by this equation. And to analyze the type of solutions, we obtain the equation of binormal directions and prove that there are 4 binormal directions, then we have 4 asymptotic directions. The differential equation can be written as follows, or you can use T, where T is the U2 over the U1, J is this matrix, and the alpha star is the matrix of the cofactors of alpha. And we now concentrate on rank 2 case. At first, P with rank of alpha equal to 2, then the rank of the cofactor matrix is 1. In this case, there is vectors W and R, such that alpha, the matrix of the cofactors can be written by using R and W. Then FAD at the point can be written in this way, and we can split and have a equation of degree 2. Then if the rank of alpha is equal to 2, by the above notation, we have alpha is M2 hyperbolic if and only if the discriminant of the before equation is greater than 0. The case M2 parabolic if and only if this is equal to 0, and the M2 elliptic if and only if this is less than 0. And the alpha is an inflection point if and only if the first factor is 0. Sorry. Then, about the solutions of the equation of the asymptotic direction, we have that we can write the equation by a complete square, and the alpha is an inflection if and only if the equation is identically 0, then all of the direction are solutions. Alpha is not an inflection point if this equation is not identically 0, and we have distinct solutions in the real projective space. Real projective space, and the multiplicity of each solution is equal to 2. In the case where alpha is M2 parabolic, if and only if the equation is equal to 0 has a unique solution with multiplicity 4, and the alpha is M2 elliptic if and only if the equation has no real solutions. Then we have a complex solution with multiplicity 2 in this case. I need some water. Then we have some problem here, because the above proposition describes that there are some cases, the hyperbolic and the parabolic case, where the real solutions are not some real solutions. This occurs because, we call these solutions by fake directions, and this occurs because some of the solutions of the asymptotic, the equation of the asymptotic direction are not related to some binormal directions. If we have the M3 set of the 3 by 3 matrices, we denote by MY the P, where the rank of alpha is equal to 2. Then we have that given a surface M, there exists a residual set O in the embeddings of the surfaces in the de Sitter space, such that for any x in this set, we have M is equal to M2 union M3. M3 is an open subset of M. M2 is a smooth curve in M. Our equation is a binary differential equation of degree 4. It's not easy to work with these equations. One way to study these equations is by lifting the directions fields defined in the plane to a lift on the surface M given by f minus 1 of 0 in R3. It's a Davidov method. If 0 is a regular value of f, then M is smooth and the projections to the plane is a fold. The critical set of this projection is called the discriminant, and its image, it's the discriminant of the equation. Then we denote here the singular set by P sigma f. The singularities of the surface f minus 1 of 0, where sigma f is given by f equal to 0 and the gradient is equal to 0. And the P of k, the discriminant curve as k, where k is given by f equal to fp equal to 0, the singularities of the projections, p. The set of the singularities of the surface is contained in this discriminant. Then, if P is a point of where alpha has rank 3, then generically the surface, we prove that this generic surface is smooth at P. Then, if we want to study the singularities, we need to study the points where the rank of alpha has rank 2. We prove that if we have the equation of the asymptotic directions, then P is of type alpha hyperbolic. If P is of type alpha hyperbolic, then the surface can have AK singularities if K is greater or equal to 3. Then it's more degenerate than we expect at the first time. And if P is of type alpha parabolic, then the surface can have singularities AK with K greater or equal to 4. The type of the singularities of this surface f minus 1 of 0 gives us the diffeomorphic shape of the surface, and so you can have it also the diffeomorphic shape of the singularity curve of the surface. We made some example also where the closed cap singularity also appears. And we wanted to study the configuration of the asymptotic direction near these spectrum points of the set of the singularity curve and also for the singularities of the projections. We try to prove that there are some maybe in the equation there are some I don't remember. If the surface has some symmetry, but we don't know about it yet, to help us to deal with the quartic equation, because this is not so easy. In this case, we have some ideas how to work, but it's difficult in general. Okay, and thank you very much for your attention. Muchas gracias. And happy birthday, Federico.
Are there any questions or comments? Okay, I have a question just to have a geometrical idea. For surfaces in R5, you have generically 5 asymptotic directions. And in this case, in R4, you know, in this case, you lose 1. Where is this appeared? What did happen to this already? In a simple way.
In the first, because the binormal direction that we are considering here are only the like. Okay. Not all the binomials. Okay? Because of this, we lose some.
Okay, no comments? Okay, thank you very much.